This video is over lesson 101, solving multi-step absolute value inequalities. So ladies and gentlemen, we went over the basics of this in lesson 91. So I've got my lesson 91 notes here. So we're going to go over this just very quickly. So remember that if we have an absolute value, in some ways what it's doing is it is taking our number line and folding it in half on itself. And so all we have essentially is the positives, and the negatives fold over onto those. So that if I say the absolute value of x is less than 3, in some ways this is saying that, well, there's my 3 and it can be less than, but then because it's folded over, where the 3 is, the negative 3 would fold over with it, and the negative 2 and the negative 1. And so the end result actually is, if we unfold it, you're going to have two boundaries, one positive, one negative, and you're going to graph the space in between them. So to look at it from a more algebraic standpoint, we will split the absolute value inequality into a positive route, so positive 3, and a negative route, negative 3. And then just like we did when we multiplied or divided by negative numbers, going the negative route ends up flipping the sign. So therefore x can be less than 3 and x is greater than negative 3. So less thans produce an and compound inequality. This could also be written like this. If it's a greater than, if we think about this being folded over on itself, then there's my 3. So greater than would send it out this way. So if we consider how this kind of folds over the number line on itself, there would be my 1 with my negative 1, my 2 with my negative 2, my 3 with my negative 3, and my 4 with my negative 4. And so then if we imagine unfolding this, again, we're going to have two boundaries, but this time the solutions are going away from the middle. And this produces an OR situation. Once again, a positive route where the symbol stays the same, and a negative route where the symbol flips. Some other things to keep in mind is that if any point in time you end up with an absolute value that it's less than a negative, well, absolute values are always positive or 0, so it can never be less than a negative. That would be no solution. If you ever end up in a situation where your absolute value is greater than a negative, well, it'll always be greater than a negative because it's positive or 0. So that would be all real numbers, would be the whole line. So those are the basics. Less thans produce an and, greater thans produce an or. Can't be less than a negative. So with that being said, I'm going to ask you now to please grab your books and open up to page 681. And we're going to look at the practice problems together. So A, we have 5 times the absolute value of x plus 6 is less than 31. Remember that absolute values are, inequalities solve basically like equations. We just have to pay attention to whether or not the sign changes. So one of the things that we're going to do in particular here is we're going to solve for the inequality the absolute value first. Solve for the absolute value first. So it means anything outside of the absolute value is what you take care of first. So SADMAP would tell me to take care of my 6 first because I'm adding it, and then take care of my 5 because we're multiplying. So if I subtract 6 on both sides, remember subtraction does not change the inequality. 31 minus 6 is 25. Divide both sides by a positive 5. Positive 5 will not change the inequality, so it's still less than. And now we're ready to finish this off. So since it's less than, it'll produce an and. Another way that we could do this, though, instead of splitting it and having a positive and negative, because it's a less than, remember an option for less thans is to write your inequality like that. So that's what I'm going to do. I'm going to make this a negative 5 is less than x, which is less than positive 5. And so when I go to graph that then, going to put 0 in the middle. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so since those are less thans, this will be an open dot, and that will be an open dot. And then make sure that this is bolded so that is obviously the solutions. Don't go crazy, but do make it obvious. That's A. Moving on to B. B has the absolute value of x over 7. And then minus 3 is greater than or equal to 1. So again, we're going to take care of everything outside of the absolute value first. So the minus 3 and the divide by 7. So I start by adding 3 to both sides. So then the absolute value of x over 7 is still greater than or equal to 4 now. And then I'm going to take this and I cancel out my division. I'm going to multiply both sides by 7. So therefore the absolute value of x is greater than or equal to 28. Greater thans with an absolute value, we'll split this up into an or. So this is either x is greater than or equal to positive 28, or x is less than or equal to a negative 28. So when I make my number line this time, I'm going to put 0 in the middle here again. 1, 2, 3. I'm going to space those out a little bit smaller actually. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I'm going to count by 7s here. So negative 7, negative 14, negative 21, negative 28, negative 35. Since this is a less than or equal to and that's a greater than or equal to, that means I'm going to have closed dots at 28. And so x is greater than 28. Well, greater than 28 would be out this way. Or x is less than a negative 28. So from the negative 28 going less than would be this way. And that's B. Moving on to C. C, we have the absolute value of x over 2 plus 5, then minus 9 is less than a negative 2. Now remember that we cannot have an absolute value that is less than a negative, but that's not the situation here because we have not solved for the absolute value yet. So we take care of everything outside of the absolute value first, which is just the 9. So when I add 9 to both sides, the absolute value of x over 2 plus 5 is less than still 7. So actually it turns out we're okay. So now I'm going to split this, and since it's a less than, it's going to be an and, or we can do that extended inequality. I like the extended inequality myself, so negative 7 is less than x over 2 plus 5, which is less than a positive 7. So to solve this, we're going to start by subtracting 5 on each side. So I'm going to have a negative 12 is less than x over 2, which is less than positive 2. And so now to finish it off, a negative 12 times 2 will be less than an x over 2 times 2, which will be less than a 2 times 2. So that's a negative 24 is less than x, which is less than 4. So this time we might not actually want 0 in the middle. We might want 0 more like here. And we might want to count by 4s. So 4, 8, 12, 16, 20, 24, 28. So negative 4, negative 8, negative 12, negative 16, negative 20, negative 24, and negative 28. Since it's just a less than, that means that I've got open dots on both 4 and negative 24. And since x is in the middle there, the solutions are in the middle here. And that's C. Well, I've got plenty of room here to make a second column, so I'm going to save a little bit of space and go to a second column. D. For letter D, we have the absolute value of x minus 9 plus 3 is less than or equal to 10. So subtract 3 on both sides. And now we have solved for the absolute value, which means we're going to split it. Again, it's a less than, just like the last problem, so I can make it a negative 7 is less than or equal to x minus 9, which is less or equal to a positive 7. Now add 9 to each side, and so a 2 is less than or equal to x, which is less than or equal to 16. So for this one, my number line, again, I'm not going to want to put 0 in the middle. I'm going to actually put 0 right over here. And then 2, 4, 6, 8, 10, 12, 14, 16, 18. That looks great. Now, since it has an or equal to, that means we'll have closed dots. Those are included as part of the solutions. And then, since x is in the middle, the solutions are in the middle. E. E says the absolute value of x over 2 plus 5 minus 9 I realized I misread C a little bit ago. I'm sure you were all saying, Mr. Burford, you missed it. So I actually did this earlier. So let's just make this C. We'll go back and relabel that E. My mistake. So we'll do C real quick here. So a negative 4 times the absolute value of x plus 9 is greater than a negative 1. All right. So coming back here and actually doing C properly, let's dive in. So SAD map, I'm going to take care of my addition first by subtracting 9 on both sides. Subtraction does not change the inequality, so this will still be greater than, but now a negative 10. And then if I divide both sides by a negative 4 to get the absolute value by itself, dividing by a negative, though, will change the inequality. Now here, to avoid having to do an improper fraction, and remember we don't like mixed numbers, I'm going to make this 2.5. I'm going to go with decimal. And so now, since this is a less than, we can make it a negative 2.5 is less than x, which is less than a positive 2.5. And so on a number line, I would probably put 0 in the middle. Go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Negative 1, negative 2, negative 3, negative 4. These will be open dots, and I'll just put them about halfway between the 2's and the 3's. And that'll work. Which brings us to F. So for letter F, I've got the absolute value of 5x minus 5, and then minus 12 is greater than a negative 2. I'll fix that a little bit Don't want it looking like a 7. All right. So outside stuff first. So I'll add 12 to both sides here. And so the absolute value of 5x minus 5 is still greater than now a 10. All right. Since it's a greater than, that means it's going to be an or. So when I split this, I'll have 5x minus 5 is greater than a positive 10, or 5x minus 5 is less than a negative 10. So solve. I'm going to add 5 to both sides here, and for that matter, both sides there. And so 5x is going to be greater than a 15 here. Over here, 5x will be less than a negative 5. Divide both sides by 5 here. Divide both sides by 5 there, and since it has a positive 5, that means this will stay as it is. Remember, there's an or in between these. So when it comes to the graph, I'm going to go maybe 0 about there. -1, -2, 1, 2, 3, 4, 1, 2, 3, 4. Since these are just less thans and greater thans, that means it'll be an open dot at 3, an open dot at -1. And since it's an or, we're just going to graph both of them. They don't have to overlap. So x is greater than 3. So if going from the 3, greater than. X is less than -1. So going from the -1, less than. And that's F. Last one is G. For letter G, NCAA rules require that the weight W of a basketball used in an NCAA men's basketball game vary no more than 1 ounce from 21 ounces. Write and solve an absolute value inequality that models the acceptable weights. What is the largest acceptable weight? So, ladies and gentlemen, remember that absolute value all by itself is distance from 0. But if we put a minus in here, then that ends up shifting it over, and it's kind of counterintuitive. Whatever we minus there, it will actually shift it over to the right. So instead of being centered on 0 and looking for a distance from 0, now we want to look at a distance from 21 ounces. So I'm going to have the absolute value of W minus 21. Now, what is that distance from 21 that's allowed? Well, you're allowed up to 1 ounce distant. So your distance can be equal to 1, or it can be less than 1. Now, since that's a less than, I can go ahead and split this to be a -1 is less than or equal to W minus 21, which is less than or equal to a positive 1. And 21 to both, well, I shouldn't say both sides, all sides. And we get 20 is less than or equal to W, which is less than or equal to 22. So finally, to answer the question, what is the largest acceptable weight? Well, the largest it can be is 22 ounces. And that, ladies and gentlemen, is the end of this lesson.